So have you ever had one of those moments where something just like clicks? You learn something new, hear a story, and boom, it's in there, part of your knowledge. But then think about, I don't know, a story someone tells you right before you fall asleep, or maybe a dream you had. Poof, gone by morning. Why is that? Why do some things stick and others just fade away?
That's what we're diving into today, this really intricate world of how memory actually forms. We're going from the tiny stuff, like how neurons talk to each other, all the way up to these like hidden automatic systems running our bodies. And the sources we've got, they offer some, well, really fascinating glimpses into neuroscience. They kind of lay out the basic mechanics shaping our thoughts and even our unconscious actions.
Yeah, and what's really fascinating, I think, is seeing how things you wouldn't expect to be connected in the brain actually are deeply interconnected. So our mission today is really to unpack all this, to figure out the fundamental ways we learn and remember, and how these systems show, well, surprising links and just how different we all are in these abilities.
Okay, let's jump in. Starting with memory itself, right?
Exactly.
Yeah.
And the sources really put a spotlight on that question you raised. Why does something really intense, say a traumatic car accident, become so vivid, last maybe a lifetime? While, maybe a similar story, but heard when you're drowsy, just vanishes, like a dream. It seems like the way the brain registers the info might be similar, but the context, the environment around it, that seems to be key for whether it sticks, its salience.
It really makes you think about people with, well, just extraordinary memory. Like Stephen Wiltshire, you know his story.
Yeah.
Autistic savant, didn't speak much from age 3. But his ability, imagine a 20-minute helicopter ride over, say, Rome or Tokyo. And then he sits down and draws the entire city. Every building, column, window, perfect proportions, correct angle, all from memory. I struggle to draw my own street from memory, let alone Rome. It just highlights how incredibly different his brain must be working, right? Mm-hmm. And it forces neuroscientists to ask, okay, what is different? Why can he do that? And, well, most of us can't.
Well, our understanding has definitely evolved over time. For a long while, the early ideas were pretty simple, like learn new fact, capital of France is Paris. Maybe you grow a whole new neuron, simple as that. Then, decades later, scientists discovered the synapse, that little gap where neurons chat. So the theory shifted. Maybe memory is about making new synapses. But now, the current view is more nuanced. It's mainly about synaptic plasticity. It's not always about building totally new stuff, but more about changing and crucially strengthening the connections that are already there, those communication points.
Right, so it's less like paving new roads and more like turning existing paths into like superhighways.
Yeah.
Which brings up that classic neuroscience saying, right? Neurons that fire together, wire together. Hebbian plasticity.
Precisely. And a really key player in this strengthening, especially for what we call long-term potentiation, or LTP, is this excitatory neurotransmitter called glutamate. If you remember one neurotransmitter, it's probably glutamate. It's central. So when a synapse gets stronger, there are a few main ways it happens. The sending neuron might release more glutamate, or the receiving neuron gets better at listening, more responsive, or it might even build more receptors to catch that glutamate signal. And there's even like a feedback loop, a clever way the receiving cell tells the sending cell, hey, let's make this connection stronger, so it knows to induce LTP too.
Okay, so these amazing tiny mechanisms are working away. But where in the brain is this happening? You often hear about the hippocampus being important for memory, and it's interesting, those savants, like people memorizing pi or drawing cities, they often talk about using a memory palace, right? Linking things to places in a familiar space, like walking through their house. It does make you think, how much is memory tied to space?
Oh, the evidence for the hippocampus being critical is pretty compelling, very strong. Take the famous case of HM. He had epilepsy, they removed his hippocampi. After that, he just couldn't form any new long-lasting memories at all. We also literally see LTP changes in the hippocampus when learning happens. And if you block LTP pharmacologically, you see the effects right there. So yeah, the hippocampus seems essential for consolidating memories, making them permanent. But, and this is important, memory isn't only in the hippocampus. LTP happens, well, all over the brain.
Oh, okay.
Yeah, in areas for emotion, for learning movements. Different kinds of memories use different networks, different storage methods.
Okay, so this strengthening helps explain why that car crash memory is so vivid it sticks, while the bedtime story just evaporates. And if memory can be strengthened, I guess it can also be weakened or disrupted. What kinds of things affect it?
Oh, definitely. Lots of things can interfere with LTP in memory. For example, hypoglycemic states, like being really, really hungry, starving even. That reduces LTP. Your body's basically saying, focus on survival now, not memorizing this.
Mm-hmm.
Then you've got stress hormones. Now, short term, they can actually give you a memory boost. You might remember every tiny detail of a scary event, right?
Yeah, that slow motion feeling.
Exactly. But chronic stress, day after day, that actually damages LTP and memory over time. So good short-term, bad long-term. And then there's alcohol, ethanol. It directly messes with LTP, especially in the hippocampus, which helps explain why you might not remember those late-night chats after a few drinks, or again, like dreams, they just don't consolidate properly.
Right, and that brings us back to, well, us individuals. If these are the mechanisms, why are we all so different? How do you get this spectrum from HM, who couldn't make new memories, to Stephen Wiltshire with his perfect recall? Where do we fit?
Well, like a lot of things in biology, it's a spectrum, and most of us land somewhere in the middle, Our individual differences come down to a mix of genetics and environment. You might have tiny genetic variations affecting how much glutamate your neurons release, or how sensitive your receptors are, or even in how your unique neural networks got built over your lifetime. All these little things add up to create your specific memory abilities.
And speaking of neural networks, it's so important to remember it's not just one neuron talking to one other neuron. The brain is this huge, unbelievably complex network. What is it, 100 billion neurons? And each one connects to thousands, tens of thousands of others. It's mind-boggling.
It really is. And that complexity creates a huge challenge.
Yeah.
Figuring out the signal versus the noise. In a system that busy, there's always random, spontaneous firing happening, like static. So a major job for the brain is telling the difference. What's a meaningful signal and what's just background noise. And this is where inhibition becomes absolutely crucial. Neurons don't just excite, they also inhibit, they quiet things down.
Okay, so how does that work? How do they quiet things down and all that chatter?
Well, there are two main kinds of inhibition that are really important. First, a neuron can actually inhibit itself. It fires its signal, then quickly shuts itself off, basically saying, okay, message sent, done now. That's called temporal sharpening. It makes the signal precise in time, stops it from blurring into noise. Second, and this is really cool, is spatial sharpening or lateral inhibition. Here, a neuron inhibits its neighbors.
Its neighbors?
Yeah. By quieting down the neurons next to it, it makes its own signals stand out more clearly, sharper, more localized. It's like shouting in a crowd. If you can get the people right next to you to be quiet for a second, your voice carries better, creates contrast.
Huh. That sounds kind of abstract, but you can actually see it, right? Like pain. That sharp pricking pain feels different from a dull ache. Is lateral inhibition involved there?
Exactly. It helps pinpoint that initial sharp sensation, then lets it fade slightly into the background.
And in vision, too. Detecting edges.
Absolutely critical for edge and contrast detection. It's basically how your brain defines the boundaries of objects. It enhances the differences. The Nobel Prize work by Hubel and Wiesel. It's foundational. They showed neurons in the visual cortex respond to specific things, like lines at certain angles, vertical lines, diagonal lines. And the brain builds up our picture of the world from these specialized neurons layer by layer. It all relies on this interplay of excitation and inhibition.
And there's that visual illusion, right? The grid where you see dark dots at the corners that aren't really there.
Yeah.
That's lateral inhibition messing with us.
That's a perfect example. It's an artifact of how your visual system processes contrast using lateral inhibition.
Or even like when you scratch around a mosquito bite to make the main itch feel less intense. Is that the same idea?
That's another great everyday example. You're stimulating the surrounding neurons, causing inhibition that reduces the sensation from the main spot. These things really are happening all the time. So, okay, tying this back to memory again. It becomes clear that memories aren't just stored in one single neuron or even one synapse. They live within these huge neural networks. Think about it. Maybe you have a neuron, let's call it neuron C, that fires if it sees an impressionist painting. Could be Monet, could be Seurat, could be Degas. It responds to the category impressionism, not just one specific painting.
So networks allow for concepts, categories.
Exactly, not just isolated facts. And when you think about memory within these rich context-representing networks, it suddenly makes sense why emotional context is so powerful, why some memories feel so much more significant. It's all embedded in how these networks are formed and interconnected. Memory is really an emergent property of these complex networks.
Okay, wow. So shifting gears a little bit here. This is where it gets really interesting, I think. We've talked about conscious thought, experiences becoming memories, but there's this whole other world inside us, running completely on autopilot, right? Often influencing memory, mood, everything. We're talking about the autonomic nervous system, the ANS. This is the stuff you don't consciously control. Heart beating, breathing, digestion, goosebumps, even things like orgasm. It just happens.
That's exactly right. And just to place it, remember the big picture. Nervous system divides into central brain and spinal cord and peripheral, everything else. Within peripheral, you have somatic, that's your voluntary muscle control, picking up that pen, feeling things. And then you have the autonomic system, controlling all those involuntary organ functions. Quick side note, somatic nerves are usually myelinated, faster signals. Autonomic are typically unmyelinated, a bit slower.
Okay.
And this autonomic system, it has two main branches, often working against each other, this sympathetic and parasympathetic. You got it. Think of them as the gas pedal and the brake pedal for your internal organs. The sympathetic system is your fight or flight. It's for arousal, alertness, emergencies, stress response.
Right. So like that hippo chasing you example. Or maybe meeting someone you're really attracted to for the first time.
Right.
Your heart pounds, breathing gets faster, blood shifts to muscles, digestion slows right down. Forget digesting lunch when you need to run. You sweat, muscles tense up, ready for action.
Exactly. Survival mode. And then the parasympathetic system is the opposite. Rest and digest. It promotes calm, growth, energy storage, repair. Think about after a huge Thanksgiving dinner, right? You just want to relax, maybe nap.
Definitely. Food coma.
That's your parasympathetic system kicking in. Heartbeat slows, blood flow goes to your gut, digestion gets stimulated, your immune system does its work. It's about building back up. Usually they work in opposition to keep things balanced, and each branch uses its main chemical messengers, neurotransmitters. For the sympathetic system, the main one hitting the target organs is norepinephrine, or NE. It revs things up, though the adrenal gland releases epinephrine, adrenaline, which is closely related. That's kind of a cool special case during stress. And for the parasympathetic, the rest and digest signal comes primarily from acetylcholine, or ATU. Now, here's a really crucial point. Sympathetic isn't always excitatory, and parasympathetic isn't always inhibitory.
Oh, okay. How does that work?
It totally depends on the organ, and specifically the type of receptor on that organ. Take the heart versus the GI tract, the gut. On the heart, sympathetic NE excites it faster beat. Parasympathetic AE inhibits its slower beat. Makes sense, right?
Yeah, gas and brake.
But on the GI tract, it flips. Sympathetic NE actually inhibits digestion, slows it down. Parasympathetic AE excites it, speeds it up.
Huh. Why the difference?
Because the organs have different types of receptors for the same neurotransmitter. Some receptors, when activated, cause excitation, others cause inhibition. The organ dictates the response based on its receptors.
Ah, okay. That explains things like beta blockers. Right. They block specific sympathetic receptors, the beta receptors, just on the heart. So your heart rate slows down, less physical stress, which is why athletes aren't allowed to use them in the Olympics. They could stay too calm under pressure.
Precisely. It targets that specific receptor interaction, shows how nuanced the system is. And sometimes these two systems don't just oppose each other, they actually have to work together, sequentially. The male reproductive system is a classic example.
Right. This is where you need both. Erection requires the parasympathetic system to be dominant, relaxation, blood flow. You need to be calm. But then, ejaculation is driven by a surge of sympathetic activity, increased heart rate, muscle contractions, that energy burst.
Exactly. And understanding this sequence helps make sense of some common issues, like erectile dysfunction, a huge chunk, maybe 60%, is linked to stress. Why? Because that sympathetic overdrive shuts down the necessary parasympathetic activity for erection. And things like premature ejaculation can be seen as maybe too rapid a switch from parasympathetic to sympathetic dominance. And this balance, or imbalance, profoundly affects our overall health too, like the immune system. Parasympathetic activity generally supports immune function, helps your body fight infections, repair tissues, but chronic sympathetic activation, chronic stress, actually suppresses the immune system.
Which is why people often get sick when they're super stressed out.
That's a big part of it, yeah. The body's resources are diverted to the perceived emergency, not long-term maintenance like immunity.
So this whole automatic system, how is it controlled? Is the brain telling it what to do? What's the hierarchy here?
There's definitely a hierarchy of control from the brain down to the ANS. You can think of it roughly in 3 levels, kind of like evolutionary layers. At the base, the oldest level, is the hypothalamus. It's all about maintaining homeostasis, that stable internal balance. Think of the bear reflex for blood pressure. If you lose blood, pressure drops, sensors tell the hypothalamus, and it kicks in the sympathetic response to compensate. Reptiles have this level.
Okay, basic survival stuff.
Right. Then in mammals, you add the limbic system on top. This adds emotion. Now, just the smell of a predator can trigger a full-blown sympathetic fight-or-flight response in a gazelle, even without any physical danger yet. Emotion drives the ANS. And then, in primates, especially humans, we have the cortex, the highest level. This means our thoughts, our memories, our anxieties about the future. They can directly activate the ANS. It's pretty amazing that just thinking about public speaking can trigger the same pounding heart and sweaty palms as facing a real physical threat. That top-down control from the cortex through the limbic system to the hypothalamus, that explains why chronic worry or negative thinking, like in depression, can keep the sympathetic system dialed up, leading to physical symptoms of stress.
It's incredible. And even this automatic system, it's not totally fixed, is it? It can change. It has plasticity, too.
Absolutely. The ANS is definitely plastic. It adapts. You see it on a molecular level. Chronic stress can actually ramp up the production of enzymes needed to make norepinephrine, making it easier to sustain that stress response. The system gears up. At the cellular level, think about sensory receptors. They can become sensitized, more responsive. Like after a scary encounter, maybe the smell of that place makes you jumpy. Or they can habituate, become less responsive over time. That spider in your room that terrified you at first. After a while, you might barely notice it. Desensitization.
Getting used to things.
Right. And maybe the most fascinating is cognitive control, like biofeedback. People can learn to consciously lower their blood pressure by thinking pleasant thoughts, right? But they're using their cortex to intentionally activate the parasympathetic pathway, dampening the sympathetic drive. It shows direct thought control over an automatic function.
What an incredible journey we've taken. From, the tiny dance of chemicals at a single synapse, through brain regions like the hippocampus, building these vast networks for memory, all the way to this hidden autonomic system that's constantly adjusting our internal state, keeping us alive.
Oh.
And seeing how it's all connected, our thoughts, our environment, our memories, our physical responses.
Yeah, if you zoom out, the big picture is really about the brain's amazing adaptability and how varied we all are. Memory isn't static, it's this dynamic thing shaped by synaptic changes and network building. And the ANS, while balancing essential functions, is also constantly being nudged by our biology, our feelings, even our thoughts. It's all intertwined.
So what does this really mean for you listening right now? Well, it helps explain maybe why some memories feel so permanent and others are fleeting. Why stress feels the way it does in your body. And maybe, just maybe, it hints at the power you have through your thoughts and focus to influence some of these seemingly automatic states. Gives you a new way to look inside, doesn't it? So here's something to think about. How does your own unique way of remembering things, shaped by your life, your genes, your experiences, how does that specific brain construct of memory influence how you see the world right now? And even how your body reacts without you thinking about it? What could understanding that mean for how you learn, grow, and connect with yourself and others?